Now, let us talk about the wave modes in detail. The wave modes have two indexes such as T0M, L0M, and FNM. You will find the torsional and the longitudinal modes have the first index of 0, but the flexural mode has n that can be 1, 2, 3, etc. The first index of 0 means that the torsional and the longitudinal modes are axial symmetric modes. The particle displacement at any point of the pipe cross-section is the same along the pipe circumference. We call this kind of a property axial symmetry. However, the particle displacement of flexural mode is not axial symmetry starting from the number 1. The second index of M is the numbering order starting from the frequency 0 Hz. This slide shows the cross-sectional area view of circumferential particle displacement of flexural modes. The first index of the flexural mode is equal to number of lines that separate the circumferential particle displacement of flexural mode. This example shows F1M that has one axis at the center, and the particle displacement is different at the opposite location. This schematic drawing explains why discrete probes along the pipe circumference generate flexural modes and have a long near-field length. The encircling probe has no near-field length because it is continuous along the pipe circumference. The slide shows a dispersion curve of 4.5 inch OD, 0.337 inch wall steel pipe. For guided wave testing, we use guided waves for field inspection. The first thing we have to know is what kind of waves are in that pipe. The dispersion curve shows the wave modes in the pipe, plotted with the frequency on the x-axis and the group velocity on the y-axis. This dispersion curve shows wave modes between 0 Hz to 100 kHz. There are so many wave modes: L01, L02, T01, F11, F12, F53, etc. And some of them are not plotted here. Those would be T02, L03, F101, F22, F101, etc. There are thousands of wave modes in this narrow frequency range, and their propagating velocities are different depending on the frequency and the wave mode. The second question is which wave mode is best for guided wave testing. We have to select one best mode and try to generate the selected wave mode instead of generating other wave modes. If we generate other wave modes besides the selected mode, those wave modes will show up as background noise because their velocity is different from the selected wave mode. For selecting one best wave mode, we have to know what our purpose of guided wave testing is. The purpose of guided wave testing is to answer the client's questions. Where is the defect and how big is it? To answer these questions, we need to find the defect in the pipeline. The two key things in finding a defect are, first, increasing signal-to-noise ratio, and second, increasing spatial resolution. The inspector can directly control spatial resolution with instrument settings, because the spatial resolution of guide wave is decided by the operating center frequency and the number of cycles. Ultrasonic testing uses a tone-burst electric pulse with a low number of cycles to increase spatial resolution. This slide shows a tone-burst signal generated by the magnetostrictive sensor system with a 64 kHz center frequency adapter. The left side plot is RF data plot with the time on the x-axis and amplitude on the y-axis. The plot shows the generated RF signal from 1 to 6 cycles. The right side plot shows the spectrum of RF signals, plotted with the frequency on the x-axis and amplitude on the y-axis. As you can see, the one-cycle RF signal has a broad spectrum, covering between 45 kHz and 90 kHz. However, the 6-cycle RF signal has a narrow band between 57 kHz and 74 kHz. To increase the spatial resolution, our transmitting signal needs to be narrow in space. Because the RF signal has a time on the x-axis and the distance is a product of the time and the velocity, the signal width in space is proportional to the signal width in time. In guide wave testings, we recommend using 1 or 2 cycles to get a narrow signal width. A narrow signal width can differentiate two neighboring indications or differentiate a defect from a geometric feature. Now, let me explain more about the spatial resolution. This slide compares the signal width of 64 kHz guide wave testing and 5 MHz ordinary UT. Using the shear wave velocity, the wavelength of 64 kHz guide wave testing is 2 inches, and the wavelength of 5 MHz UT is 0.026 inches. The guide wave testing signal width comes from the probe design itself. The 2-inch wide iron cobalt strip is built with 2 quarter wavelength element pairs spanning that width, driven by a single one-cycle electrical pulse, producing a signal width of 4 inches. This is a fixed property of a probe adapter design, not something that depends on how far away a reflector is. By comparison, the 5 MHz UT signal width is about 0.051 inches. The GWT signal is about 78 times wider than UT signal. What is the problem if a signal width is wide? The wider the signal, the worse the spatial resolution, meaning it becomes harder to separate two closely spaced indications. How do we define spatial resolution? We borrow the definition used in optics. Assume two identical reflectors at two adjacent positions, in this case 2 inches apart. Check the signal amplitude at each reflector's peak, and the amplitude at the midpoint between them. If the amplitude at each peak is at least twice the amplitude at the midpoint, we conclude the two indications are resolved as separate. In this example, the defect is located 2 inches from a weld. Because of the round-trip travel distance, the reflected wave from the weld and the defect appear 4 inches apart in the recorded data. Using the one-cycle 64 kHz signal, whose signal width is 4 inches by probe design, and checking the video signal, the rectified envelope signal, rather than raw RF signal, the two indications are just resolved as separate. This is a borderline case, not a wide margins. This is why guide wave testing should use one cycle to achieve the high spatial resolution needed to find a defect near geometric feature. If attenuation is high, using 2 cycles is an acceptable trade-off to increase signal amplitude, even though spatial resolution is somewhat reduced. As a long-range ultrasonic testing method, the GWT should find the defect near geometric feature, such as a pipe spot and weld. If guide wave testing uses more than 2 cycles, the large reflecting signal from a geometric feature will hide the signal from a defect near that feature due to poor spatial resolution. This is the main reason the guide wave report should include per indication and detailed section report for checking signal-to-noise ratio and spatial resolution. This slide shows the RF plot and its spectrum plot. Any RF waveform can be transformed into the frequency domain using fast Fourier transform. The spectrum plot shows the frequency distribution of the RF signal. For example, if you hear hello from a handphone, you recognize who is calling if the caller is your close friend. Your brain uses this spectrum analysis of the voice to recognize who is calling. Now we can tell that hello is not a single frequency. It is a broadband. In the same way, a 5 MHz transducer generated broadband signal with a 5 MHz as its center frequency. This slide shows the RF signal of 64 kHz center frequency on the left and its spectrum plot on the right. As you can see, the spectrum shows a broadband signal between 40 kHz and 90 kHz. Now, let us move back to the dispersion curve of the 4.5-inch OD and 0.337-inch wall steel pipe. This dispersion curve has a frequency on the x-axis, so we can place the spectrum plot on the transmitting RF signal directly onto it. Let us consider that we use the 1-cycle 64 kHz RF signal as the transmitting wave. We can then bring the spectrum plot of that RF signal into the dispersion curve. With the spectrum of RF signal now placed on the dispersion curve, we can see exactly which wave modes are actually present in the transmitted signal. There are many wave modes in this dispersion curve, but we only consider two, one non-dispersive mode and one dispersive mode. We selected the T01 mode as a non-dispersive mode and F22 mode as the dispersive mode. T01 mode has a constant velocity, but F22 mode has a velocity depending on frequency. The Flexural mode F22 has velocity that varies with the frequency and its value increases as the frequency increases. If you look at all the wave modes in the plot, you will find that T01 mode is the only non-dispersive wave mode for frequencies between 0 and 100 kHz.